Hello, and welcome to the Nocturnal Astronomer. I'm Atlas Reid, your guide through the cosmos. Tonight, we embark on a remarkable voyage through time, tracing the birth of our planet Earth from nothing more than cosmic dust and gas floating in the darkness of space. We'll witness how gravity sculpted a fiery ball of molten rock, how a catastrophic collision gave us our moon, and how the very air you're breathing came to be. This is a story written in stone, told through meteorites and ancient rocks, a tale 4.5 billion years in the making. If you enjoy these types of videos, please give this one a thumbs up and subscribe to the channel for more soothing space explorations. I'd love to know, where are you watching from tonight, and what time is it where you are? Drop a comment below. Let's dive in. Our story begins approximately 4.6 billion years ago, in a region of space that bore no resemblance to the orderly solar system we know today. Picture, if you will, a massive cloud of gas and dust drifting through the galaxy, a nebula enriched with elements forged in the hearts of previous generations of stars. This solar nebula stretched across billions of kilometers, a cold, dark expanse where hydrogen and helium mixed with heavier elements like carbon, oxygen, and iron. This cloud wasn't uniform. Like cream swirling in coffee, denser pockets of material existed within the nebula. Scientists have determined through careful study of meteorites that something disturbed this peaceful cloud, perhaps the shock wave from a nearby supernova explosion. That disturbance triggered a process that would eventually lead to our existence. The cloud began to collapse under its own gravity, a slow, inexorable gathering of material that took millions of years to unfold. As the cloud collapsed, something interesting happened. The laws of physics dictated that as the material drew inward, it began to spin. Think of an ice skater pulling in their arms during a spin, rotating faster and faster. The solar nebula behaved in much the same way. As it contracted, its rotation accelerated, and the cloud began to flatten into a disk shape, much like pizza dough spinning in the air. At the center of this disk, where most of the mass concentrated, pressure and temperature began to rise dramatically. The material packed together so tightly that atoms started to collide with tremendous force. The core grew hotter and hotter, reaching temperatures of millions of degrees. Eventually, the conditions became so extreme that hydrogen atoms began fusing together to form helium, releasing enormous amounts of energy. This was the moment our sun ignited, transforming from a dark clump of gas into a brilliant star. The young sun was different from the stable star we see today. It was more active, more violent, with powerful stellar winds that would play a crucial role in shaping the planets to come. Meanwhile, in the disk of materials surrounding the newborn sun, the first seeds of planets were taking shape. The disk wasn't smooth but filled with countless particles of dust and ice, ranging from microscopic grains to pebbles. These particles orbited the young sun at slightly different speeds depending on their distance from the center. This difference in orbital velocity meant that particles constantly bumped into each other. Sometimes they bounced apart, but often, especially with smaller particles, they stuck together through electrostatic forces, similar to how dust clings to a television screen. Through this process of accretion, dust grains combined to form larger clumps. These clumps collided with other clumps, forming pebbles. Pebbles joined to create boulders. The process continued, slowly but relentlessly, over millions of years. The disk around our sun was becoming less uniform, with certain regions developing concentrations of material that would eventually become planets. The temperature of the disk varied greatly depending on distance from the sun close to our young star. The intense heat vaporized lighter materials like water ice and methane. Only materials with high melting points, such as metals and silicate rocks, could remain solid in the inner solar system. This is why the inner planets, including Earth, are rocky. Farther out, beyond what scientists call the frost line, temperatures were low enough for ice to remain solid. This allowed the outer planets to grow much larger, accumulating vast amounts of frozen material along with gases. As millions of years passed in the spinning disk around our young sun, the boulder-sized clumps of material continued their patient accumulation. Eventually, through countless collisions and gravitational attraction, some of these grew to sizes measured in kilometers rather than meters. Scientists call these larger bodies planetesimals, the building blocks of planets. These weren't uniform spheres like modern planets, but irregular chunks of rock and metal tumbling through space. The planetesimals that formed in Earth's region of the solar system, about 150 million kilometers from the Sun, consisted primarily of silicate rocks and metallic elements like iron and nickel. Unlike the icy planetesimals forming farther out in the colder regions of the solar system, these inner system bodies were dry and rocky, shaped by the intense heat radiating from the young sun. As planetesimals grew larger, their gravitational pull increased. This created a feedback effect, a runaway process where the bigger an object became, the more effectively it could attract nearby material. The largest planetesimals began to dominate their orbital neighborhoods, sweeping up smaller bodies in their paths like cosmic vacuum cleaners. Through this process, the thousands of planetesimals that once filled the inner solar system gradually consolidated into just a handful of larger bodies. Around 4,500 million years ago, one of these growing bodies would eventually become our Earth. At this stage, Proto-Earth was far from the planet we know. It was a world under constant bombardment, with planetesimals of all sizes raining down upon its surface. Each impact released tremendous energy. When a planetesimal struck the surface, the kinetic energy of motion converted instantly into heat, like rubbing your hands together but on an unimaginable scale. These impacts didn't just add mass to the growing planet. They fundamentally shaped its internal structure. The bombardment generated so much heat that Proto-Earth's interior began to melt. This created what scientists call a magma ocean, a global layer of molten rock extending hundreds of kilometers beneath the surface. Current research using isotopic dating of meteorites suggests that this phase of Earth's growth lasted somewhere between 10 and 100 million years, though the exact timeline remains an area of active scientific inquiry. During this molten phase, something crucial occurred. The laws of physics dictated that denser materials would sink toward the center while lighter materials rose to the surface. Iron and nickel, being much denser than silicate rocks, began a gradual descent through the molten interior. This process, sometimes called the iron catastrophe, resulted in the separation of Earth into distinct layers. The heavy metals accumulated at the center, forming Earth's core. The lighter silicate rocks remained closer to the surface, eventually forming the mantle and crust. This differentiation into layers had profound consequences for Earth's future. The metallic core would eventually generate the planet's magnetic field, a shield protecting the surface from harmful solar radiation. Without this magnetic field, life as we know it would likely never have developed. The layered structure also enabled plate tectonics, the process that continually renews Earth's surface and plays a vital role in regulating climate over geological timescales. The young Earth during this period was nothing like the blue marble we see from space today. Its surface glowed red with heat from countless impacts and the molten rock below. There were no oceans, no atmosphere as we would recognize it, no continents. Just a hellish world of molten stone and metal, constantly reshaped by the violence of formation. Yet within this chaos, the seeds of our future home were being planted, layer by layer, impact by impact, as gravity and physics worked their patient alchemy. Earth's formation might have proceeded relatively peacefully from this point, gradually cooling and solidifying over millions of years. But approximately 4,500 million years ago, something catastrophic happened that would forever change our planet's destiny and give us one of the most beautiful sights in our night sky. Another planetary body, roughly the size of Mars, was following an orbit through the inner solar system. Scientists have named this vanished world Theia, after the Greek goddess who gave birth to Selene, the goddess of the moon. Based on computer simulations and analysis of lunar samples, researchers believe Theia formed either in a similar region of the solar nebula as Earth or possibly at one of the gravitationally stable points in Earth's orbit. Over time, gravitational interactions with other bodies in the forming solar system altered Theia's path. Its orbit became increasingly unstable until eventually, the inevitable occurred. Theia collided with Proto-Earth in what remains one of the most violent events in our planet's history. The impact happened at an oblique angle rather than head-on, with Theia striking Earth's surface at a velocity of several kilometers per second. The energy released by this collision staggers the imagination. In an instant, both worlds were partially vaporized. Rock that had been solid became gas. The outer layers of both planets were blasted into space, creating an expanding cloud of molten droplets and vaporized stone. Some of this material escaped the Earth-Theia system entirely, lost forever to space. But much of it remained trapped in orbit around what was left of Proto-Earth, held by gravity into a ring of debris encircling the battered planet. The collision had several crucial effects beyond simply increasing Earth's mass. First, it dramatically increased Earth's rotation rate. Before the impact, Proto-Earth probably rotated once every 5 to 6 hours. The angular momentum imparted by Theia's glancing blow set Earth spinning even faster initially, though this rotation would gradually slow over billions of years due to tidal interactions with the Moon. Second, the impact redistributed material between the two worlds, mixing their mantles while leaving their metallic cores largely intact. Perhaps most importantly for life's eventual emergence, the collision's energy was so intense that it created a global magma ocean on Earth's surface. The entire planet became molten once again, erasing all evidence of its earlier surface features. For perhaps 2 million years after the impact, Earth was enveloped in a thick atmosphere of rock vapor. As this rock vapor gradually condensed, it released enormous amounts of heat, preventing the surface from cooling quickly. The planet glowed with its own light, radiating heat into space like a dying ember. Meanwhile, the debris ring around Earth began its own transformation. Gravity works on all scales, and the countless fragments in orbit started to clump together, just as the original planetesimals had in the solar nebula. The process was remarkably fast by geological standards. Some recent simulations suggest that the Moon could have formed in a matter of hours to thousands of years after the impact, though other models propose longer timescales. The newly formed Moon was initially much closer to Earth than it is today, perhaps only 20,000 kilometers away compared to its current distance of 384,000 kilometers. It appeared enormous in the sky, many times larger than we see it now. The gravitational interaction between Earth and its new companion was intense, causing tremendous tides that flexed and heated both bodies. Over billions of years, tidal forces have gradually pushed the Moon away from Earth at a rate of about 4 centimeters per year, a process that continues even today. After the chaos of the giant impact, Earth entered a period that scientists call the Hadean Aeon, named after Hades, the Greek underworld. This name captures perfectly the hellish conditions that prevailed on our planet during this time, roughly 4,500,000,000 to 4 billion years ago. The surface remained far too hot for solid rock to form, covered instead by a global ocean of molten magma that glowed red in the darkness of space. The magma ocean wasn't uniform in depth. Current models suggest it may have extended down several hundred kilometers, perhaps as deep as 1,000 kilometers in some regions. Below this molten layer, the pressure was so immense that the rock remained solid despite the extreme temperatures, forming the beginnings of Earth's deep mantle. Convection currents churned through the magma ocean, hot material rising from below while cooler material sank, creating a constant roiling motion like a pot of boiling water scaled up to planetary dimensions. Cooling a planet the size of Earth is not a quick process. The rate at which heat could escape into space was limited by the thick atmosphere that surrounded the young planet. This atmosphere, quite different from the one we breathe today, consisted primarily of water vapor along with carbon dioxide, nitrogen, and smaller amounts of other gases. These gases had been released from the molten rock through a process called outgassing, similar to how bubbles form in boiling water as dissolved gases escape. The water vapor was particularly important in controlling Earth's cooling rate. Like a blanket trapping heat, the dense steam atmosphere acted as a powerful greenhouse, preventing rapid heat loss to space. Earth's surface temperature during this period may have hovered around 800 to 1,000 degrees Celsius. Under these conditions, water could not exist as a liquid on the surface, remaining instead as vapor in the atmosphere. As millions of years passed, the magma ocean gradually solidified from the bottom up. This happened because the melting point of silicate rocks increases with pressure. Deep in Earth's interior, the pressure was so great that despite the high temperatures, the rock reached a point where it could no longer remain molten. A solid layer began to form at the base of the magma ocean, slowly growing upward like ice forming on the surface of a pond, but in reverse. Eventually, perhaps 2 million years after the moon-forming impact, the solidification process reached Earth's surface. For the first time since the Great Collision, the planet had a solid crust. This early crust was likely quite thin and unstable, constantly being broken up and recycled back into the partially molten interior below. Imagine a surface covered with dark, basaltic rock, fractured and glowing red from the heat beneath. Once the surface solidified enough to lower the surface temperature below the boiling point of water, the thick steam atmosphere began to condense. Rain started to fall, but this was unlike any rain seen in billions of years since. The raindrops sizzled and evaporated the moment they touched the superheated rock, creating vast clouds of steam that rose back into the atmosphere only to condense and fall again. This cycle repeated countless times, each time removing a bit more heat from the surface. Gradually, over thousands or perhaps tens of thousands of years, the surface cooled enough that water could remain liquid. The rain fell and finally stayed, pooling in low areas and depressions in the new crust. The first oceans began to form. These were not the blue oceans we know today, but likely had a greenish or brownish tint due to dissolved minerals and iron compounds. The early ocean was probably quite hot, perhaps close to 100 degrees Celsius, but it was liquid water nonetheless, a crucial ingredient for life. With a solid surface and the first accumulations of liquid water, Earth entered a new phase of its development. The planet was still hostile to life as we know it, but it was no longer the hellish world of the Hadean. The formation of a stable atmosphere and ocean would prove crucial for everything that followed, including the eventual emergence of biology. Scientists distinguish between Earth's primary and secondary atmospheres. The primary atmosphere, if it ever existed, would have been composed mainly of hydrogen and helium captured directly from the solar nebula during Earth's formation. However, the young sun's intense radiation and powerful stellar winds likely stripped away any primordial atmosphere early in Earth's history. The atmosphere we need to understand is the secondary one, formed through volcanic outgassing from Earth's interior. Every time a volcano erupts on modern Earth, it releases gases from deep within the planet. The same process occurred with far greater intensity on the young Earth, as volcanic activity was much more vigorous than today. The gases released included water vapor, carbon dioxide, nitrogen, sulfur dioxide, and smaller amounts of other compounds. Importantly, these volcanic emissions contained virtually no free oxygen, the gas that makes up 21% of our current atmosphere. The composition of Earth's early atmosphere remained very different from today's for billions of years. Carbon dioxide was far more abundant, perhaps accounting for most of the atmosphere apart from nitrogen and water vapor. This thick carbon dioxide atmosphere created a strong greenhouse effect, keeping surface temperatures warm even as the sun was about 30% dimmer than it is now. Scientists call this puzzle of how early Earth remained warm despite a fainter sun the faint young sun paradox, and the greenhouse effect from carbon dioxide and other gases provides the most likely solution. The source of Earth's water has been a subject of considerable scientific debate. For many years, researchers believed that water arrived primarily from comets, those icy visitors from the outer solar system. However, recent studies comparing the isotopic composition of water in comets, asteroids, and Earth's oceans have revealed a more nuanced picture. The deuterium to hydrogen ratio, a sort of fingerprint that varies between different sources of water in the solar system, suggests that Earth's water came from multiple sources. Current evidence points to a combination of water delivered by impacts from water-rich asteroids from the outer regions of the asteroid belt and water that was present in the materials that originally accreted to form Earth. Some water may have existed in hydrated minerals within the planetesimals that built our planet. When these planetesimals were heated during Earth's formation, the water would have been released and eventually made its way to the surface through volcanic activity. By approximately 4 billion years ago, based on evidence from ancient zircon crystals found in Western Australia, Earth had both a solid crust and liquid water oceans. These zircon crystals, some of the oldest materials ever found on Earth, formed in the presence of water, providing direct evidence that oceans existed remarkably early in our planet's history. This finding surprised many scientists, who had expected that Earth's surface took longer to cool sufficiently for liquid water to be stable. The early oceans were probably quite acidic due to the large amounts of carbon dioxide dissolved from the atmosphere. As rainwater fell through the carbon dioxide-rich air, it formed carbonic acid, similar to carbonated water but much more concentrated. This acidic water was highly reactive, rapidly weathering rocks on the young continents. The weathering process released various elements into the ocean, including sodium, calcium, and magnesium, beginning the process of making seawater salty. Interestingly, evidence suggests that the ocean has maintained roughly similar salinity levels throughout most of Earth's history, despite the constant input of dissolved materials from weathering. While the early Earth had a solid crust within a few 100 million years of its formation, this crust was quite different from the continents we stand on today. The distinction between oceanic and continental crust represents one of the fundamental features of our planet, and understanding how continents formed tells us much about Earth's geological evolution. Oceanic crust, the type that underlies ocean basins, forms continuously even today at mid-ocean ridges. Here, molten rock from the mantle rises up and solidifies, creating new seafloor. This oceanic crust is relatively thin, averaging about 7 kilometers in thickness, and is composed primarily of basalt, a dark, dense volcanic rock. More importantly, oceanic crust is constantly recycled. As tectonic plates move, old oceanic crust is pushed back into the mantle at subduction zones, where it melts and is eventually recycled. This means that virtually no oceanic crust on Earth today is older than 200 million years, a mere blink in geological time. Continental crust is fundamentally different. It is much thicker, averaging 30 to 50 kilometers, and is composed of less dense rocks, primarily granite and related rocks rich in silica. Most crucially, continental crust is buoyant compared to oceanic crust. Like foam floating on water, continental crust is too light to be pulled down into the mantle by subduction. This means that once continental crust forms, it tends to remain at the surface, accumulating and amalgamating over billions of years. The oldest known continental rocks on Earth are the Atlas Reid in northwestern Canada, dated to about 4 billion years ago. However, individual mineral grains called zircons found in Western Australia are even older, with some dating back to 400 million years. These ancient zircons crystallized from molten rock in the presence of water, indicating that not only did continental crust exist very early in Earth's history, but so did liquid water oceans. The question of how continental crust first formed remains an area of active research, but scientists have developed several complementary theories. In the very early Earth, when the planet's interior was much hotter than today, volcanic activity was far more intense. Some researchers propose that mantle plumes, massive upwellings of hot rock from deep within the planet, rose to the surface and melted partially. This partial melting is key because it naturally separates lighter, silica-rich minerals from denser ones. The lighter material, being less dense, would rise to form protocontinents while the denser material sank back into the mantle. Another important process in creating continental crust involves the recycling of oceanic crust at subduction zones. When oceanic crust is pushed down into the mantle, the increasing pressure and temperature cause it to release water and other volatiles. These fluids rise into the overlying mantle wedge, lowering its melting point and causing partial melting. The resulting magma is less dense and more silica-rich than the original oceanic crust. This magma rises toward the surface, sometimes erupting from volcanoes, sometimes cooling underground to form granite. Over time, this process can build up significant volumes of continental crust. Evidence suggests that the rate of continental crust formation was not constant throughout Earth's history. There appears to have been a peak in crustal growth between 3 and 2.5 billion years ago, during a period of dramatic geological change. Before about 3 billion years ago, Earth's continental crust may have been predominantly mafic, meaning it was denser and darker than modern continental crust. After this transition period, continental crust became more felsic, richer in silica and lighter in color and density, resembling the granite-dominated continents we know today. Earth is unique among the planets in our solar system in possessing active plate tectonics. This geological process, where large segments of the crust move slowly over the underlying mantle, profoundly shapes our planet's surface and plays a crucial role in regulating climate and supporting life. But plate tectonics didn't begin immediately when Earth formed. Understanding when and how this process started remains one of the most debated questions in geology. Plate tectonics requires specific conditions to operate. The crust must be rigid enough to form distinct plates, yet the underlying mantle must be able to flow slowly over geological timescales. There must be dense oceanic crust that can sink into the mantle, initiating subduction. The planet must also be losing enough internal heat that convection currents in the mantle are vigorous enough to move the plates. In the very early Earth, conditions were quite different from today, and the style of tectonics may have been different as well. One challenge in determining when plate tectonics began is that the process erases much of its own evidence. At subduction zones, old oceanic crust is pulled down into the mantle where it melts and is recycled. This means that direct evidence of ancient seafloor spreading is extremely rare. Similarly, the constant creation and destruction of crust at plate boundaries means that the oldest continental rocks have often been deformed, metamorphosed, and altered beyond easy interpretation. Despite these challenges, geologists have assembled various lines of evidence to constrain when plate tectonics might have begun operating in a manner similar to today. One approach involves looking for specific rock types and geological structures that form only in plate tectonic settings. For example, rocks called ophiolites, which represent slices of oceanic crust and upper mantle that have been thrust up onto continents, provide direct evidence of ancient ocean basins. The oldest confirmed ophiolites date back to about 3 billion years ago. Another telltale sign of plate tectonics is paired metamorphic belts. When an oceanic plate subducts beneath a continent, two distinct zones of metamorphism develop. Near the subduction zone, rocks are subjected to high pressure but relatively low temperature, creating one type of metamorphic rock. Farther inland, above where the subducting plate releases fluids and causes melting, rocks experience high-temperature metamorphism. These paired belts of different metamorphic rocks are characteristic of subduction zones and have been identified in rocks dating back about 700 million years with certainty, though some researchers claim to have found older examples. The chemistry of ancient rocks also provides clues. Certain patterns in trace elements and isotopes are characteristic of rocks formed in subduction zone settings. Analysis of rocks between 3 billion, 800 million, and 2 billion, 700 million years ago shows that some have subduction-related chemical signatures while others formed in non-subduction settings. This coexistence of different magma types suggests that while some form of plate recycling may have been occurring, it may not have been operating globally as it does today. Many researchers now favor the view that plate tectonics began operating in a modern style sometime between 3 billion and 2.5 billion years ago. Before this time, Earth's interior was hotter, and the crust may have been too weak to form rigid plates. Instead, the planet may have operated under a different tectonic regime, perhaps one where the crust behaved more like a thick, stagnant lid periodically broken up by rising mantle plumes, or where smaller, shorter-lived episodes of subduction occurred without the continuous, planet-wide system we see today. The transition to plate tectonics had profound implications for Earth's evolution. It established a mechanism for recycling carbon dioxide between the surface and interior, helping to regulate climate over billion-year timescales. It created diverse geological environments where different minerals and rock types could form. And it may have been crucial for the development and evolution of life. By 2.5 billion years ago, the major pieces of Earth's geological puzzle were falling into place. The planet had cooled sufficiently that a stable crust could persist. Oceans covered much of the surface, though they were arranged quite differently than today. Plate tectonics was operating, moving fragments of continental crust around the globe and creating a cycle of supercontinent formation and breakup. The stage was set for the Earth we know. The continents that existed in Earth's early history bear little resemblance to the familiar shapes of modern continents. Through the constant motion of plate tectonics, continents collide, merge, and split apart over hundreds of millions of years. Scientists have identified several ancient supercontinents, vast land masses where most or all of Earth's continental crust was assembled into a single massive continent. The oldest proposed supercontinent, called Valbara, may have existed around 3 billion years ago, though evidence for it remains fragmentary. Better documented is Kinnerland, which appears to have formed around 2,700 million years ago and broken apart about 2,500 million years ago. After Kinnerland's breakup, the continental fragments eventually reassembled into another supercontinent called Columbia or Nuna, which existed from about 1,800 million to 1,500 million years ago. This pattern of assembly and dispersal would continue throughout Earth's history, with the most recent supercontinent, Pangaea, beginning to break apart just 200 million years ago, ultimately forming the familiar arrangement of continents we see today. The formation and breakup of supercontinents has significant effects on Earth's climate and environment. When continents cluster together into a supercontinent, there is less coastline relative to land area, which affects ocean circulation patterns. The interior of a supercontinent tends to experience extreme temperature variations and low rainfall, creating vast deserts. When a supercontinent breaks apart, rifting creates new ocean basins, and increased volcanic activity at the spreading centers can affect atmospheric composition. As Earth's surface evolved, so did its atmosphere. For the first 2 billion years of Earth's history, the atmosphere contained little to no free oxygen. This changed dramatically around 2,400 million years ago in what scientists call the Great Oxidation Event. Photosynthetic organisms, primarily cyanobacteria, had been producing oxygen as a waste product for hundreds of millions of years. Initially, this oxygen reacted with dissolved iron in the oceans and reduced minerals on land, effectively being scrubbed from the atmosphere. Eventually, these oxygen sinks became saturated. The iron in the oceans had been oxidized and precipitated out, forming distinctive bands of iron-rich rock called banded iron formations. With nowhere else to go, oxygen began accumulating in the atmosphere, fundamentally changing Earth's chemistry and paving the way for the evolution of more complex life forms that could harness this reactive gas for more efficient metabolism. From our vantage point 4.5 billion years later, we can trace Earth's remarkable journey from a disk of dust and gas to the dynamic, life-supporting planet we inhabit. Every aspect of our world, from the solid ground beneath our feet to the air we breathe, is the product of billions of years of geological processes. The water in our oceans has been recycled through the rock cycle countless times. The continents we live on are fragments of ancient supercontinents, reassembled in new configurations. Even the atoms in our bodies were forged in stars that died long before our solar system formed. And on that note, our journey through Earth's formation comes to a close. Thank you for joining me on this voyage through deep time. I hope you found it both enlightening and calming. Until next time, this is Atlas Reid reminding you to look up at the stars and remember the incredible story written in the rocks beneath your feet.